All right. All right. Let's move on. And let's introduce a new player, which are F of R theories. F of R theories. So this is a set of another set of scalar tensor theories of modified gravity that can again be linked to dark energy. We have seen, right? To conformal transformations, we can play this role. And the idea here is to generalize basically Einstein theory, Einstein gravity, if you wish, right? Because what Hilbert did was to just introduce the Hilbert, the Einstein, we have the Einstein-Hilbert Lagrangian, which is just minus square root of G times the simplest scalar that you can possibly have, containing second-order derivatives of the metric, which are given in the curvature. Okay, so it's a theory based on the Riemann curvature. You have contraction of contractions that gives you a scalar, which is the Ricci tensor. That's the simplest scalar that I came up with, and magically it works. Okay, so nature is relatively simple, or looks like relatively simple. Okay, but why R? The idea now is to go to a Lagrangian, which is more general. We want to be more general. And therefore, what we could do, the simplest generalization that we can do, again, we keep this guy that we need to have an invariant volume, and then an F of R term. So, where here, F for the Einstein-Hilbert action, we had that F of R equal to R, identity. So if you want, this is an F of R theory with F equal to the identity. But the idea is to, let's generalize it. Let's make it more general. And if we want to write the most general theory of gravity, okay, then what we could have? Well, we can have R, this would be GR, but we want to make it more general. Therefore, we could have another F of R. It's not the same here, okay? Just another function, it could be whatever. And you can think it is F of R, you can Taylor expand it, for example. Then what would you get? You will get an R term. Well, actually, I could also do like this. F of R, so we can Taylor expand it, so that at zeroth order we have an R, and then alpha R square, then plus beta R to the power of 3, plus. Okay, plus something else, and I'm continuing here, because this is just a subset. You see, this is just R multiplied by a factor with a certain power. It's quite limited. We can be even more general, because this is all based on the Ricci tensor. But we could have, for example, terms of this sort. R mu, R mu, or even sigma, R mu, R mu, plus invent whatever you want. Okay? All these terms tend to lead to instabilities. Basically, certainly. In instabilities. That is because it's very likely that you end up with equation of motions that are higher than second order derivatives. Okay, then higher than second order, third order, fourth order, and so on and so forth. And they are very likely to give you instabilities, okay? Basically, certainly. Okay? That's why basically all physics you see arrives at equation of motions that are up to second order. Okay? Whereas this guy here, this is simple. and it has been largely studied. Okay, basically all theories of f of r have been kind of understood, almost. Okay, at least in a general sense. Okay, and you understand that this f of r can contain gr, and they are a generalization because you can have those additional terms. The simplest and the first f of r theory that have been ever invented, which was not even called f of r theory. We are going back, it's even before inflation, so it was not even invented to solve inflation or to explain inflation, as we are going to see later, that you're going to speak about that later in the seminar. But it was used as a toy model to investigate deviations from GR. Okay? And the Lagrangian was of this sort. So you see, just the first two order. So in a f of r at second order. Okay? That's what we have. This would be Starobinsky. Starobinsky. Okay. Nice. And you can notice, I mean, we're going to see more later on that, but you see that there is a power of 2, and R, with the expansion of the universe, tend to grow, right? Therefore, there are epochs in which R is negligible. So it's like the standard GR, and there are instead deviations where R is larger, and that is going to dominate, to rule the universe. Okay? Nice. Let's give a look now at our f of R Lagrangian, and let's give a look at the equation of motion that we would expect. So what we have? Well, we have our action. Let's write it down. Root of G, and then f of r. So I'm not taking care about the matter and so on, just the gravity sector I'm investigating, and then we go for the variation of the metric, of the action, to identify the equation of motion. Okay, so just list action principle. I'm not going to do all steps because most of them are identical to what you have done in GR, so there is no new fancy stuff coming up. But what I'm going to do is to highlight the differences. Okay, so that you see where the differences are popping up. That's easy to be done because we have the action, right? We have the variation of the action that the delta is going to act on this guy here, right? Therefore, we need to work out the square root, the variation of the square root of minus g of f of r. We have a product, therefore product rule of derivatives. Therefore, f of r, variation of square root of minus g, plus square root of minus g, variation of f of r. So we have two terms here, 1 and 2. Okay? Now, term number 1. This is kind of standard, okay? Because it looks like what we have in general relativity, except that of having an R here, we have an f of r. Therefore, this guy is sort of standard, at least in terms of the mathematics that one is going through, because instead of r, the only difference is that all those terms are going to be f of r, just that. Okay, so we get an f of r factor. Instead of just r. Then for the term number 2 is sort of newish, in the sense that we can split it into parts. One is kind of similar to the one we have in GR, so no differences, whereas the other one is completely new. Okay, that is not in a general relativity at all. So this is going to be newish. because the term 2 is going to be equal to what? Square root of minus g, the f over the r variation of r. Okay? That's this term. The variation of f is equal to this guy here. So the derivative with respect to r, because this is a function of r, variation of r. Okay? But what is r? Yes, it's a scalar, but it's the contraction of a tensor. And the contraction contains the metric. Therefore, it's the metric times tensor. Product rule of derivatives. We have two terms that are popping up. Therefore, we are going to get square root of minus g, f prime of delta g mu nu r mu nu. So you can see the contraction that is taking place here from the Ricci tensor to the Ricci scalar, plus square root of minus g. Oh, sorry, I already took it out. So it's going to be g mu nu, and then the variation of r mu nu. Okay, where I called f prime is just the derivative of f with respect to r. And again, I recall that r, so the Ricci scalar, is equal to g mu nu r mu nu. Okay? Nice. So we have two terms. Remember there is an f to the minus 1 in front. So we have a term 2a and a term, again with the f prime in front, which we call 2b. Nice. So the 2a is the standard one. Okay? Again, with the standard, I mean that you need to follow exactly the same path that you use in general relativity, but with an f prime factor in front. That's what you get in GR. You have a f prime in front. The path of the mathematics is exactly the same. Okay? Then what we have? 2b. The other guy, and that's new. That's completely new. New. No iPhones, that's new. And therefore, our g mu nu variation of r mu nu in GR, wait, let me go, damn it, need space. So remember that in GR, when we are dealing with that term, it's going to vanish, because it's going to end up to represent a total differential. You use your Gauss theorem. This gives you a border term that is going to disappear. Okay? So in GR, that term is not there, but not here. Because here there is this f to the minus 1 in front that doesn't give you a total differential, and that term will survive. Let's see. So we are at 2b. So 2b, new. So we have that basically in GR, we have the integral of the omega square root of minus g mu nu, and then we have a total differential. So we have basically, it can be rewritten as f mu nu comma mu. That's invariant, as it should be, and this guy disappears. You do an integration by part. You use Gauss theorem. You get a border term that you neglect. Okay? This guy is completely irrelevant for the study of the equation of motion. Whereas now, in f of r, that's different, because you get a term which is, again, to look similar to, what is this mu? No mu here, okay, it's just the determinant minus the determinant of the metric. We have an f to the minus 1 in front of this guy. Okay, it can be rephrased in terms of this, differential, whereas here there is the f to the minus 1 in front. This is not a total differential. You cannot apply Gauss theorem. Therefore, this guy survives. That's why this is new. You don't have this guy in GR. Okay? Good. Now that we know the key differences, it's kind of easy, if you want, to identify the equation of motion. Okay? So the f of r field equations. Not the Einstein field equations, but it's a generalization of the Einstein field equations. So we are going to have r mu nu minus 1/2 r g mu nu. Right? That would be the Einstein tensor. That what? The r term gets modified with an f prime factor. You see? That's the standard path. R is going to be multiplied by an f prime of r. Then we have the Ricci scalar that is going to gain an f term. Okay, so this is from 2a, this is from 1. And then what? Well, we have the new guy. And if we write it explicitly, it's going to be the mu, the covariant derivative of mu, covariant derivative with respect to nu, f prime of r plus g mu nu, box f prime of r. Equal to of k to the power of 2 t mu nu. That's how it gets. These are your new field equations. A little bit more complicated than what we had before. And it contains GR. Okay? GR is a subset of f of r theories. Okay? And in fact, no, that's it. Okay? GR is a subset. Just one of the, is the simplest case of f of r theories, if you wish. Okay? Nice. Now, another little subtlety, because in GR, yeah?
Can you introduce the cosmological constant in geometric formalism?
Yeah, you can basically construct, you see, you have these additional terms that then could give you rise to something similar to the cosmological constant. Okay, that's why f of r theories are also tried to explain, to replace dark energy with a modified gravity. Okay, now, yeah? Sorry? The second yellow term. Sorry, plus. Yeah, you're right. I forgot the plus. Hmm?
Standard GR, you replace the f of r by r. And so so you shouldn't have the R because the F of R just gives you an R.
Sorry again, I didn't get it.
So it's under the R you replace F of R by R.
Yes?
And then
This gives you a 1.
and the second term you should delete the R.
Oh yeah. I mistook to, because I don't remember by heart, I copied, I might have made a mistake there. I guess it's a prime. That's, let me check this. Okay, I will check this out. Okay, thanks. Okay, good. Anyway, you got the idea, okay? You get, the key point is that you get factors that are coming because of f up there, and a new, completely new term that is coming from the fact that this is not anymore a total differential. And that's completely new stuff, okay? That's completely new stuff is the thing that contains most of the thing that can give you the acceleration expansion in your universe. Now there is, just to mention it, in GR, what you do, I put it here because it's a side note. So in GR, you can, typically the derivation that you do is to define your connection, gamma, and you identify it with the Christoffel symbols, right? You do that because it's based on assumptions, okay? You get unique whenever you assume metric compatibility and torsion free, right? Metric compatibility and torsion free. Therefore, this guy is unique, okay? You get the Christoffel symbols, and this is not a dynamical field. Not a dynamical field, it's just a function, okay? Not a dynamical field. But there is another approach that you could do. You can say, okay, let's be slightly more general, and we let our connection to be a field, so dynamical. In this way, you go through the Palatini, okay? That's the Palatini formalism. Palatini. And in GR, several times this is not thought. For example, I don't, because if you do that, you get exactly the Einstein field equations. Okay? No difference. But that's not the case in F of R theories. Okay? So in F of R, this guy, if you let the connection to be an independent field, then you get different equations of motions. So in GR, you can leave it as dynamical field. You get the Einstein field equations. In F of R theories, if you do that, you don't get those field equations. You get a different set. Okay? Just as a side comment. Okay, good. So, of course, I will stick to this one. Okay, we will keep the affine connections not as a dynamical field. So we will always use the Einstein formalism. So with the affine connection as not being a dynamical field. Okay. No, because you can, that's to be more general, because basically in GR you apply the constraints, those two constraints to, I mean, initially it was given because it kind of made sense, in the sense that it's kind of intuitive, because for example, with metric compatibility, basically tells you that if you have a scalar product, and if you are free-falling, you're falling a geodesic or something, the scalar product is going to be always the same. Otherwise, you would have an additional tensor, the non-metric compatibility tensor, that will give you variation of the angles as you're moving along geodesics. Okay? And Einstein said, I'm falling, if I have a vector, why should I see something doing like that? Okay? So intuitively, he kept it fixed. So this was like the first, but it's not necessary after all. Okay? In GR, so with that action. Okay, so that's related to the action. If you let an f of r, then you get those additional terms, and that's going to make things more complicated. Okay, so the two formalism, Palatini and Einstein, will give you different results, different equations of motion. All right. Okay. Don't know if I managed to finish today. Anyway, let's try. So, let's give a look at a few examples. Okay. Possible f of r theories. One I already introduced, which is this one, Starobisky. So it's kind of good for inflation, but it screws up the rest. Okay, basically it's okay, but not good for dark energy. So you cannot use it to explain late time acceleration, only early time acceleration. Then you might have f of r, which is r plus 1 over r, which would be relevant at early time, at later times, okay? Therefore, it would be good for dark energy, in the sense that you get an acceleration at later time. But during matter domination, you get a singularity. One over r. When this is 0, the gas explodes. Doesn't work. Okay? Not a good theory. A good theory, or one that can stand the evidence of nature and do not have singularities. Minus mu Rc. These two are two different constants. So mu is a constant of the theory, Rc is a constant of the theory. G, okay, is a constant of the theory for Newtonian gravity. Okay, or GR as G as a parameter. These one are two other parameters. Okay, mu R over Rc to the n, and then we have R over Rc to the power of 2n plus 1. So you see that this is a family of theories because we can have n 1, 2, 3, and so on and so forth. Okay? R and Rc are parameters. Okay, mu is dimensional, it's just a number which carry no dimension. And we can see right away that there is no singularity. If R can be equal to 0, doesn't matter, there is a plus 1. It doesn't blow up. Okay? No singularity. So we don't even need to look at the equation of motion to realize that. If R is small, that's the case for the pass, then f of r goes to R, standard GR. If 2, if 3, then the other fact, if R is large, then f of r, you can look at the limit of this function, goes to R mu minus R C. How does it look like? That's the cosmological constant. Okay, we have R and then a constant factor. Remember, these are constant of the theory. Ok? Quindi you get mu, whenever mu Rc, you can set it equal to lambda, obeying the observations that we have. We have something that is similar. You see, this is a limit, so it's not equality, that's a limit. We get something that behaves like the cosmological constant. That answers your, replies to your question with one specific theory. Okay? So f of r theory can be used to explain accelerated expansion. Then what happens? Well, we can start to classify the theory. How do we do it? Well, we go through the usual study of the phase space. Okay? Usual torture that I already exposed you for several times, so I'm going to keep it short now. But in any case, what we're going to do is to consider a Friedman, Lamette, Robertson, and Walker metric, where our Riemann curvature is equal to 6, 2h squared plus h dot. We are going to consider our function f, so our f of r theory. We are going to consider matter. We are going to consider radiation. And I will call basically the derivative of f with respect to r as big R. So the f prime of before I will call it with big F. Okay, so these holds all over the places. What we do, you see that we have an f of r, so we don't have Einstein gravity, we have to redo cosmology. And if we redo cosmology, I will not write the equations because it's pointless. We rederive Friedman equations where it will containing additional terms of the sort h to the power of 3 and h to the power of 4. Doesn't matter the shape of the equation, it's completely irrelevant, okay? Just redo cosmology and you get it. Then, what we have to do, again, phase space, we are going to use the phase space. After we have the Friedman equations, you remember, again with flat cosmology, we have an expression of omega m equal to 1 minus x1, minus x2, minus x3, and so on, representing the energy density of the components of the universe which is not matter. Okay? Therefore, same business that we did before. We define now, and we can identify an f dot hf, an x2, which is f over 6f h squared, and x3, which is an r over 6h to the power of 2, and the one for radiation, which now is k squared r over 3f h squared. Okay, that's omega radiation. So what we have in addition of what we had before? We had a term now that we can reconvey with matter, with the dark energy. So again, with these modified Friedman equations, we basically get 1 minus x1 minus x2 minus x3 minus x4. Okay? Matter is here. Radiation is here. You can see the modification of the Friedman equation popping up here. We have an F here that before we hadn't. And then we have this guy here, which is associated to omega phi. Okay? So we can interpret it omega phi as x1 plus x2 plus x3 as, let's call it, the energy density associated to the f of r theory, or if you want, that's equivalent to the omega, would be the equivalent of the energy density of dark energy. Okay? All these terms play the role of dark energy, the acceleration that you would like to have in the end. Okay? Then what you do? You do the usual business, which is the identification of the critical points. You have your first order differential equation that you turn in a collection of first order differential equations, right? Therefore, you're going to have your dx1 over the n, and then you have your function, whatever it is, dx2 over the n equal to whatever function, dx2 over the n equal to whatever function, no, m3, and then the last one, the x4 over the n equal to the whatever function. Okay, you find it in the script. Again, how it looks like is completely irrelevant. Then you find the critical solutions. Critical solutions means that you get the xe over the n equal to 0, and you identify the critical points. You get the critical points. There is quite a pile of them. I'm not going to derive them. The only thing that I want to stress is a term that is popping up in these equations. Okay? They are function of x1, x2, x3, and x4, and r. Okay? That's a little bit annoying. That's a little bit annoying. So in general, you get just your dxe over the n. That I call that n is the number of e-folding. So that's basically the variable that tells you that is tracing the expansion, the time evolution of your universe, of the universe. And this is a function, how do I call it? Well, that's a function of is a function of x1, x2, x3, x4, and r. So what you need to do now is to get rid of this r, or better to say, to express this equation such that you get only the x1, x2, and x4, 3 and 4 parameters that characterizes the phase space. Okay? Therefore, these guys that contain this m function can be captured in this guy. Is the ln f over the ln r. Okay, so this is just a definition. I define m as the logarithm derivative of the logarithm of f. That's it. If we do that, this is equal to r, f, comma, r, r. Remember that f is a derivative of r prime. Okay, this r comes from the logarithm here over f, comma, r. And as I said, we have this r, which is annoying, this r is contained here, and that's annoying. We don't have a self-contained set of equations. Okay, that set of equations is not self-contained. But we can realize the following. We can realize that if we define now this r as minus the ln f over the ln r, so this was the derivative with respect to r of f, this is straight away f. Okay? We realize the fact that, again, just by the construction of the logarithm derivative of a logarithm, we just have that. Okay, what we had before, but without the additional derivative. And if we use our FR, we can just realize the fact that this guy is equal to x3 over x2. Okay, this comes from the fact, this is a bit of a detail that is not really telling us anything about physics, but that's, look, we have x2, which is equal to that. Then we have x3, which contains the h squared to the power of 2. You see? So what we can do, we can get this right, so basically we bring h2, h to the power of 2 on the other side, and x3 here. So we have h to the power of 2, which is a function of r and h3. We plug it here, and we basically, and the r magically disappears. So this guy is a function of r. Now that we have this expression, we can use it here, okay? We have our r, you see, that we plug up there. Here. And once we do that, we get this expression, which is x3 over x2, f comma r over f comma to the power of 2 r, which is just a function, as you see, of x3 and x2. Okay? So, again, and I'm going to close. We are just following the usual path for the phase space study, where the phase space parameters are going to be these ones, in this case. You see a modification of the Friedman equations because f of r theory we are redoing is not GR, therefore we are redoing cosmology, and we get additional terms, you see? We have f here, f here, f here. Okay, that's the imprint of the non-GR gravity that we are using. Omega m, as usually, is coming from the revised Friedman equations, read like that. This is depending on radiation, that's radiation. This is matter. Therefore, this guy, in flat cosmology, that's why there is a 1 here, there is not a curvature term, there is a 1. We get this guy that we can identify as the energy density up due to the modified gravity, or if you wish, what would be associated, if you think in terms of a fluid, of your dark energy. Okay? Then we want to study the critical points. We want to first transform the second order differential equation that we have for our Klein-Gordon equations into a first order differential equations. We have our set of 4 equations, and we have the annoying fact that we have R explicitly involved in those expressions. Then we need to get rid of in some way. And the way we do it is the following. So we just define the logarithm, the logarithm derivative of the logarithm of f, which is this guy here. Then we look for the logarithm, the derivative, so the logarithm derivative of the logarithm derivative of little f, which is this guy, and an r pops up. Okay? But we have expressions that we can use from the definition of x2 and x3, and we discover that, sorry, all of this is equal to the ratio between x3 and x2. Therefore, we have an expression of r that we plug here, and this expression of r that we plug here depends only on x3 and x2. So, also this function that apparently looks like a function of m is actually a function of x2 and x3. Therefore, all of these equations depends on the parameters of the phase space. Boom, we can do the rest. Identify the critical points, see which kind, if they correspond to matter domination, radiation domination, acceleration, or some weird other stuff of matter, for example, the one with the equation of state equal to 1. And then we need, once we have that, this is anticipating what we are going to do the next lecture. What we want to do is to identify the F of R theories that make sense. Because you have so much freedom that you can generate whatever comes to your mind, okay? The F of R theory that makes sense is the one that gives you a universe where you start with, no, that's not used, is R. We start with radiation, goes to matter domination, and then with a final acceleration. And there are constraints on F such that you obtain this chain. So that you go from one critical point to another one in the right sequence. Okay? And we are going to see that we can define a parameter space where we have M and R as a parameter. For you see, the first derivatives of F and the second derivative of F gives you a range of possibilities where this is fulfilled. If you are, and this simplifies out your life. It's going to be a triangle, as we are going to see, and the theories that are here are, yeah, you can use them. If you get a theory here, and a theory here would mean that it has is too steep or not steep enough, and it is too curved or not curved enough. Okay? And it is why you are sure that it's nonsense and you just throw it away. Okay? But this is for the next lecture. Good. So we can conclude here, at least in the morning. Today is going to be a long day. Later we are going to have 2 talks in the seminar. So I give you the time to eat, and then we can resume again here in this lecture, and we are going to learn something about Starobinsky. So you are going to present something, and you are going to present something. What was it? We even discussed it, I forgot. Back reaction, right, sorry. Back reaction. So we are going to see how the back reaction term could lead the deviation from, or let's say could be a term that people forgot about, okay? To take it, but more details are going to be given later. Okay, thank you very much, and I'll see you later. Guten Appetit.